like alkenes, alkynes can undergo hydroboration, such as is shown here. If you use simple borane reagents, it leads to these vinyl boranes and then further hydroborations involving the additional boron-hydrogen bonds. What's very commonly done in practice, however, is to not use borane itself, but rather use sterically hindered dialkyl boranes, such as the compound shown here. The two alkyl groups already bonded to boron mean there's only a single reactive boron-hydrogen bond. And sterics lead this reaction to result in boron attached to the terminal carbon of the triple bond. Now, these can be quite useful. They undergo oxidation in the same fashion as alkyl boranes to replace the boron with a hydroxyl group. But of course, in the case of a vinyl borane, that replacement of the boron with a hydroxyl group, it leads to an enol, which, as we've learned previously, rapidly tautomerize to a carbonyl, and this means this leads to aldehyde products. So here's an example of a previously synthesized vinyl borane of this long chain alkyne undergoing oxidation with basic hydrogen peroxide and leading to the aldehyde product. So if we think about the two hydration reactions that we've examined for alkynes, one being hydration using mercury salts under acidic conditions, and now thinking of hydroboration oxidation sequence as a net hydration reaction, we have complementary synthetic methods. The reaction with mercury salts in acidic aqueous media leads to Markovnikov addition of water and thus ketones. And if this happens on a terminal alkyne, you end up with a ketone where one of the groups attached to the carbonyl is a methyl or a methyl ketone. On the other hand, if you carry out the hydroboration oxidation using a sterically hindered borane followed by basic hydrogen peroxide, you get anti-Markovnikov addition of water leading to an enol, which tautomerizes to an aldehyde. And so we have tools for doing hydration either way with terminal alkynes. Another extremely important addition to alkenes is the addition of hydrogen under catalytic systems. And these are widely used in industry and in the research lab, where hydrogen gas is the reagent in the presence of some sort of metal catalyst. And there are a wide variety of these that are available. Many involve precious metals such as platinum and palladium, but there are others that are more common metals such as rhodium and nickel. These are heterogeneous reactions. These catalysts almost always are used in solid form and hydrogen in gas, but the alkene in solution phase. And so very heterogeneous reaction mixtures. The overall process is very simple: addition of hydrogen to each of the carbons of the alkene. So the alkene is reduced to an alkane. And we can see a couple more examples of that down here. This last example is particularly instructive of the stereochemistry of the reaction. So here we're treating this dimethyl cyclohexene with hydrogen over a platinum oxide catalyst. You very often find that these reactions use acetic acid for the solvent in the reaction. And the acetic acid plays no reactive role in the process. It just happens to be a very good solvent when using hydrogen gas. Here are the two hydrogens that have been added to that double bond, and we can see from the stereochemistry of the product that those hydrogens seem to have been added in a syn fashion, each of them added to the same face of the double bond. The reason for that syn addition is that this is a reaction that takes place on the surface of the metal catalyst. And so we can depict it using these representations of the metal surface These sort of greenish colored spheres are representing the metal atoms, be them platinum or palladium or nickel or rhodium. And the sequence that occurs is first hydrogen actually reacts with the metal surface. So here we have hydrogen molecules in solution, and some of those hydrogen molecules end up bonded to the metal surface, and that as individual hydrogen atoms on the surface. The alkene then coordinates with the surface. The pi bond of the alkene interacts with the metal, and then we get very rapid transfer of two hydrogen atoms to this coordinated alkene so that those two hydrogen atoms are added to the same face. The addition occurs so quickly that there's no time for conformational change and ending up with stereochemistries other than syn addition. Before we leave this slide, it's worth noting here that we typically don't write a mechanism for this reaction using curved arrows because of the way that the reaction is mediated by the metal surface. The experiments that tell us that the syn addition occurs are represented by these sorts of reactions. There are isotopically labeled studies where H2 gas is replaced with deuterium gas, D2. Recall that deuterium is just a heavier isotope of hydrogen, but chemically identical to hydrogen 1. Here taking place on a palladium carbon catalyst. You'll very often see this designation, palladium/C. And what that refers to is metallic palladium that has been deposited on the surface of graphite, carbon in the form of graphite. The 10% refers to the weight percent of palladium on the graphite. But this is a solid material. In this case, because we're using D2, we can spectroscopically determine the stereochemistry of the product, and it's found that 100% of the product has those deuteriums having the cis arrangement on the ring. So that again tells us that we're getting syn addition across that double bond. Another way of probing this is with molecules such as this one, which are sterically hindered. In this case, there's a methyl group poised in this bicyclic compound that effectively blocks the top face of the double bond. And so we don't get any reaction of hydrogen adding to the top face as it's drawn here, the double bond. The hydrogen adds exclusively to the bottom face of this. And so when the hydrogenation occurs and the two hydrogens are added, we end up finding those two hydrogens in the final product on this face of the compound. And again, this is evidence of the syn addition of the two hydrogens to the same face of the double bond. Just as alkenes undergo a hydrogenation, alkynes will also. And two equivalents of hydrogen will react with a triple bond using similar catalysts, and again, reducing the compounds all the way down to the alkane oxidation state. These typically are very easy to do. They're done under the same sorts of conditions that we see for the alkenes with very high yields. Presumably that previous reduction passes through the alkene. So the triple bond is reduced to a double bond, which is immediately reduced to the single bond. Is it possible to stop the reduction of an alkyne kind of halfway at the alkene stage? And the answer is yes. And there are actually two different ways of doing it. So this is sometimes referred to as a partial hydrogenation, in that we're going from alkyne to alkene and not continuing on to the alkane. One way of doing the hydrogenation is to use what's referred to as a poisoned catalyst. This is a catalyst that has been somewhat deactivated so that it will carry out the first reduction of the triple bond to the double bond, but it's incapable of catalyzing the further reduction of the alkene into the alkane. There are a lot of these catalysts available. One of the more common ones is one that's referred to by its inventor's name. It's known as Lindlar's catalyst. It's a rather complex mixture of palladium that has been deposited on solid barium sulfate and then doped with this nitrogen compound called quinoline. You often simply see that written this way, where we have an alkyne treated with hydrogen gas and Lindlar palladium. So all of this is sometimes referred to simply as Lindlar palladium. And we end up producing cis alkenes in that reaction. There are other catalysts that can be employed. Nicoboride is a catalyst that will also affect this syn addition of hydrogen to a triple bond to produce alkenes. Notice the stereochemistry. In each case here, we're getting syn addition, and this is consistent with this reaction, like the reaction of alkenes, taking place on the surface of a catalyst and the two hydrogens being added to one face, in this case, one face of the triple bond, leading to the cis alkene product. If you want to reduce a triple bond to a trans alkene, a different method is available. And this one does not involve a catalyst. This one involves a reagent of sodium dissolved in liquid ammonia. And it's usually written this way, sodium slice NH3, sodium metal in liquid ammonia. Now, this is a curious mixture that you're probably unfamiliar with at this point, but sodium metal, solid sodium metal, will in fact dissolve in liquid ammonia. So the overall reaction is the reduction of a triple bond into the trans alkene. And here's a simple example of that. Now, this one is far more complex than the reaction on the surface of a catalyst. And so we're going to walk through the mechanism of this. So here is the mechanism, and let me lead you through. And this is a curious mechanism of a type that we've not seen before because it involves both single electron and double electron movements. The whole process begins by a one electron reduction of the alkyne. The sodium here is simply acting as a reducing agent, something you can probably recall from general chemistry. So one electron is donated into a pi bond. That addition into the pi bond breaks the pi bond and produces an intermediate known as a radical anion. So notice we now have two bonds between the carbons, an odd electron on one carbon and a pair of electrons, and thus a negative charge on another carbon. This carbanion is actually a very strong Bronsted base and deprotonates ammonia, which is not only a solvent but also a reactant in this process. That protonation leads to this compound, which is now a radical. So here's the proton that we've added. We still have that odd electron on carbon. And the next step in the mechanism is another reduction. Sodium adds an electron into the singly occupied orbital where the radical is to produce a pair of electrons and a new carbanion. And just like the first carbanion, this is this powerful Bronsted base and deprotonates a molecule of ammonia. And this leads to the product. It's this protonation step that leads to the trans stereochemistry because that's the most stable steric structure that can be produced. So that finishes our reactions for Chapter 11. Here is the usual list of practice problems. Focus your attention on these problems as you study and try to complete as many of these problems as you can.